Welcome to solverfy.
Hello everyone, I'm doing problem 30 of chapter 31. This question concerns the proton-proton chain, which is a fusion reaction describing the energy output of our sun. So the question refers us to formula 31.6, which I've reproduced here, which gives us three reaction equations that describe the fusion process. And each one has each reaction here is associated with a release of energy given in brackets here. And this released energy is in fact the Q value that the question is asking us about. So we're also given some values from the appendix, which I'll discuss in a moment. And we know that Q, the energy, is associated with delta M, which is the difference of mass between the elements or the items on the right side of the arrow and the mass of the elements or the components on the left side of the arrow, multiplied by the speed of light squared, c squared. So for this problem, we're basically budgeting energy, and we can rewrite these reaction equations in terms of Q here. So let's start. Write the Q value for A. So we're going to do the masses, the energy associated with the masses on the left side minus those on the right side. So here we have two protons. Let's say 2m sub p multiplied by c squared minus the mass of deuteron sub d times c squared minus the mass of the positron, which is in fact equal to the mass of the electron, by c squared. And the neutrino doesn't have an atomic mass, so it doesn't show up in this equation. And now we can see the c squared is present in every term, so we can factor that out. So I'll just quickly rewrite this. And now we want to look at our numbers from Appendix B to fill in the values. So I will convert to text for readability. And we want to be careful here because the text of the textbook tells us that we're dealing with nuclei here. So we don't want to take the H quantity because that includes an electron. So here we really want the mass of the proton. X means times. And this is given to us in atomic mass units U, and we always want to be sure to mark the units because they can really keep us from making mistakes. And we'll take the deuteron. And the electron mass. Oh, already forgetting my units here. We want all of this to be multiplied by c squared. And now you'll note that our units are in atomic mass units times c squared, whereas our final answer, we're looking for it to be in mega electron volts. So we'll need a conversion factor, which is 931.5 electron volts per c squared per u. And so you can check that the units all cancel out to give us the result in megaelectron volts. And you can put that into a calculator and verify that it does in fact equal close to 0.42 megaelectron volts. Equals approximately, I'll do a curly equal here. Now for B, we proceed in a similar way, where we write our equation, our expression for Q by subtracting the items on the right side of the arrow from those on the left side. Now, you'll notice that this time I'm marking M sub H for hydrogen, and I will explain that in just a moment. Plus a mass of deuteron, but again, I'll put deuterium instead of M sub D as I did up here. This is isotope of helium. So before we fill in the numbers, just note a subtlety here. We're dealing with nuclei, but for the case of helium, which I'm sorry is cut off here, but I'll enter the values in a second and you'll see them. But for the case of helium in the appendix, we are only given the atomic mass, which includes electrons. But since electrons in this equation are balanced, that is, the nuclei on the left side of the arrow are each associated with an electron. So this side, there's, if we're including electrons, we have 2 electrons, and the nuclei over here is also associated with 2 electrons. So we can add 2 electrons to both sides of the equation, and they cancel out. So that's why we're considering the mass of hydrogen here and not just the mass of the proton. Similarly for deuterium instead of just deuteron. So let's fill in our numbers. Oh, and again, gamma doesn't factor into the mass part here. Minus the mass of helium, which is 3.016029 atomic mass units. We'll multiply all of this by c squared, and again by our conversion factor to get megaelectron volts. And again, we can put this into a calculator and obtain a Q similar to 5.49, or essentially 5.49. Great. Now for the final equation, let's do C. Again, write our expression for Q. We have 2 times the mass of this helium isotope minus the mass of helium, times C squared, minus the mass of helium, minus 2 times the mass of hydrogen, where again we note that the electrons are balanced here, so we can add the electrons and subtract them here. So we will take the mass of hydrogen. Let's fill in the values with Appendix B. I'm just going to, hopefully you don't get confused, I'm going to try to enter them here, just for the sake of visibility up above. Minus 4.002603 U minus 2 times 1.007825 U. Again, multiply everything by C squared and by our conversion factor. And putting that into our calculator, we should get a Q value. Sorry, it's a little bit cramped here. A Q value of 12.86. Mega electron volts.